Hello, welcome to a brand new chapter where we're going to take a look at what happens when you slice through a cone, because depending on the angle you choose to slice through the cone with will result in you getting a different type of curve. So the first type of curve you can obtain is when you start with a cone and you choose to slice through it, so the angle you're slicing through it is parallel to the points that are either furthest to the right on the cone or furthest to the left. So for instance, I could choose to slice through the cone like this, because then the angle of my slice is parallel to all the points on this side of the cone, furthest to the right. If you then pull apart the two sections you've created and look at the edge of the cross section, then you will see a curve, one that looks something like this. And this type of curve is actually one that's very familiar. It's called a parabola, and as you probably already guessed just by looking at the graph alone, it's one that we're very used to by now. It's the classic quadratic. In this case, as it's a vertically placed one, we'd end up with a curve of the form y equals x squared. However, in the conic sections chapter for further maths A level, generally the types of parabolas we're going to be dealing with are going to be of a slightly different format. Instead of being vertical like we're used to usually seeing them, they're going to be on their side, or to be more precise, effectively reflected in the line y equals x. And therefore, they're going to have an equation of the form y squared equals 4 lots of a lots of x, where a is an important number that can define certain characteristics about the quadratic we're looking at. Of course, because the curve has been reflected in the line y equals x and now looks the way it does, that is why it's the y that's being squared rather than the x, which is what's usually being squared, of course. But what is this value a, and what characteristics does it define about the curve? Well, one of the useful things it can help us find is the parametric equations for the parabola. If you got a parabola of the form y squared equals 4ax, then it means you immediately know the parametric equations for that same curve could be of this format here. However, interestingly, in this chapter, you're going to have to get used to parametric equations being presented in a different way. Instead of being listed as two separate equations, one for the x and one for the y, they're often in this chapter represented as coordinates. Which seems weird, except when you think about it, that's all parametric equations ever were. They're just equations for the coordinates based on a third variable. Algebraic coordinates, if you will. Another important aspect about the curve that the parameter a can define is it tells us information about a very special point related to the curve. The name of this special point is the focus. And if you're listening carefully to what I said a few seconds ago, you would have heard that I was very careful with my wording because I didn't say this point is on the curve, because it's not. It's just a point that's near to the curve. But why has math decided to give a special name to a point that isn't even on the curve? Why do we care about it? Well, unfortunately, I'm going to have to leave part of that explanation to a future video, because some of the mathematical significance behind why we've given this special name to this special point is wrapped up in the definitions of some other things that we're not going to come across until later. But I can, at least for the moment, give you an application of why the focus is something we care about in the wider world. For instance, you could have a mirror that's shaped like the curve of a parabola, and it could therefore look something like this, and I've also decided to indicate on this diagram the position of the focus for the particular parabola curve I've drawn. But once you have this mirror shaped like a parabola, if you choose to shine some light on the mirror, any of the rays of light that are travelling in a direction parallel to the line of symmetry, so for instance in this case something like this, then interestingly, all of those rays of light are guaranteed to reflect off the mirror in a way so they'll always be guaranteed to end up travelling through the focus. So therefore, interestingly, for this parabola, any horizontal ray of light, no matter where it is guaranteed to reflect off the mirror and go through that focus. So I could have one over here, or I could have one over here, and no matter what, you'll have that same effect of the reflection going towards the focus. This is interesting because this property influences the design of satellite dishes. Most satellite dishes in the real world are shaped like parabolas because of the fact that the shape of the parabola can help reflect any of the signals the satellite dish is trying to pick up into one location, which is then where the receiver is placed so that the satellite dish can pick up a strong signal. But anyway, we're not going to be using this characteristic of the focus that much in maths for the moment, but at least it shows why it's interesting. But something useful I can tell you about the focus right now is the position of it, because the coordinates of the focus is guaranteed to be at a0 if you have a parabola of the form y squared equals 4ax. So once again, the parameter a has come in useful to define certain things about the curve. And the last important feature of a parabola that we're going to talk about today is something called the directrix. Sadly, once again, I can't fully go into what a directrix is now until we've done some further definitions in a future video, but for the moment what I can tell you is that it's a line that's placed in a specific location related to where the focus and the curve are. So it's worth pointing out the location of the focus, the directrix, and the curve itself are all interconnected. Just so you have an idea of what that would look like though, here is an example of a parabola, its focus, and then the line that's the directrix is the purple line that I've indicated with the label. For the moment, all you need to know is that for the types of parabola we're looking at, the directrix will always have an equation of the form x plus a equals 0, again showing the importance of the value of a. Cool! Let's take a look at some quick examples, because all this stuff that we've shown so far really is as straightforward as identifying the value of a and then using that in the facts we mentioned before. For question 1, they've given us the equation of a curve y squared equals 8x, at which point we might go, oh, of course, that looks like the equation of a parabola. So we can compare it to the generic format for the equation of a parabola that we gave earlier, y squared equals 4ax, and by comparing the two, we'll very quickly realise that 4a must equal 8, so therefore a must equal 2. As soon as we have the value of a, then we can just plug that value into the facts we just defined, which says therefore the coordinates of the focus must be a0, so therefore for our particular question the focus is at the point 2, 0. And the equation of the directrix was x plus a equals 0, so the equation of the directrix in this case is x plus 2 equals 0. It really is that easy. Before you get your hopes up too much, these things would only be worth 1 mark each, but it's still interesting to note that the easiest stuff in this chapter really is super easy. Moving on to question 2, you might initially look at it and think we haven't been given enough information, because instead of being given a curve, we've only been given 1 point on the curve. We do at least know it's a parabola, but still, that doesn't seem like much information. That is, until you remember the advice I gave earlier, which was that to remember that parametric equations are often disguised as coordinates. So these coordinates are actually parametric equations, and they do link up with the generic parametric equations we're given for parabolas in general, which is at squared to at. So if we compare our coordinates to the generic structure for the coordinates, we can see that therefore the value of a in this case must be 9. So therefore you're not always looking out for an equation of a curve, sometimes you're looking for the parametric equations which are written in the format of coordinates in a lot of questions. But once again, once you know the value of a, well, you can use that to find other bits of information. For instance, now we know the value of a, we can actually find the Cartesian equation of the parabola because we know it should be y squared equals 4ax, but now we know that a is equal to 9, it's therefore going to be y squared equals 4 lots of 9, which is 36 lots of x. And similarly, therefore, once we know a, we instantly know the coordinates of the focus, it would be in this case 9, 0. So there you go. But we're not done yet, because I want to introduce you to a second curve that can also be discovered by slicing through a cone. But this time we're not just going to have one cone, we're going to have 2 cones, and we're going to place them so that their vertices are pointing towards each other, like you can see on the screen right now. And then we're going to slice through the cones, but this time we're going to slice through them at a different angle. Instead of slicing through the cone at an angle that's parallel to the edge of the cone, we're now going to slice through at an angle that's steeper than that. For instance, we could choose to slice through the cone fully vertically, like this. If you then separate the sections and once again look at the edge of the cross section, this will form a curve that we can call a hyperbola. Except hyperbola is quite a general term, and for the moment we're going to look at a particular type of hyperbola called a rectangular hyperbola. And that's because it's actually a curve you've also already come across before. You might be able to guess it already just by thinking about a graph that you've come across before that involved two separate parts of the graph being completely unconnected to each other. And therefore, if you thought about that for a while, you might realize, wait a minute, isn't that what y equals 1 over x does? And you'd be right. Y equals 1 over x is an example of a rectangular hyperbola. However, just like the parabola, we're going to focus on a particular structure for our equation for the rectangular hyperbola, and the structure for that will be x times by y equals c squared. And once again, this new letter c is just a letter that we use to define a parameter, which is useful for discovering certain characteristics about this curve. You will of course recognize that y equals 1 over x is actually a special case of this, because it's just where we've rearranged to make y the subject of the formula, and it's when c is specifically equal to 1. But what characteristics can we define? Ultimately, the same characteristics we already talked about for the parabola. We can define the parametric equations for the rectangular hyperbola because they are going to be ct and c over t. So once you know what c is, you know what the parametric equations are going to be, or vice versa. And then interestingly, a rectangular hyperbola has more than one focus. It has two of them, and therefore the plural of the word focus is foci. And the foci are at these two pairs of coordinates. And then also we're going to look at the directrix for a rectangular hyperbola, except a rectangular hyperbola has two of those as well. And if you have more than one directrix, we call it directrices. The equations of the directrices for a rectangular hyperbola are this. Once again, I'd like to remind you that I'll be talking about what a focus and a directrix actually is from a mathematical perspective in a future video. What I can say for now is that actually a focus has a slightly different use in the real world compared to the focus of a parabola. Because unlike the parabola, the focus of a hyperbola is not a place where all rays of light will reflect to on the curve. Instead, the foci for a hyperbola are useful in the real world because they can show where light refracts to if you have a lens shaped like a hyperbola. But anyway, let's look at some quick examples, because once again, this stuff is actually deceptively easy. For this question, we're given that xy equals 5, which means we can compare it to the general structure of a rectangular hyperbola to find out that therefore c must equal root 5. You could technically choose c to be equal to minus root 5, but it doesn't really matter, and therefore it's easier to pick the positive one. But even if you did pick the negative value for c, the formulas are all done in a very symmetrical way, so that you'll get the same answer either way. But anyway, once you've found the value of c, you can then plug it into the formula to find the coordinates of the foci, because we said earlier that the coordinates of the foci will be plus or minus the coordinates root 2c, root 2c. So then of course that means the coordinates of our foci will be plus or minus the coordinates root 2, root 5, root 2, root 5. Of course though, that can be simplified to just plus or minus root 10, root 10. So there you go, that's the coordinates of the foci for this rectangular hyperbola. On to question 2, same sort of thing, but this time they've given the parametric equations disguised as coordinates. We can very clearly see that the value of c must be 6, because the generic coordinates for a rectangular hyperbola are this. And therefore, once we've identified what c is, we can find the equations of the directrices, because they're just going to be x plus y equals plus or minus root 2c, which in this case will be plus or minus 6 lots of root 2, and therefore we're done, we've found the directrices. But one last thing I want to tell you is that, good news, all the formulas we've shown today are all given in the A-level formula booklet, which you must be super happy about because it makes this stuff even easier still. In general, this chapter is one that's mostly going to be one that's using skills you already have from Maths A-level, or just making use of a formula that's given to you in the formula booklet. So it's actually quite a nice chapter when it comes to revision. So that will do us for today's video, but as I already said, I'm still yet to tell you why the focus and directrix are mathematically significant, so I do hope you stay tuned for the video where I go through that. Alright, see you in a future video, goodbye.